Let's now think about some real arms, starting with some very, very simple things like a Revolute, single Revolute link. Then we'll move on to something a little bit more complicated. So a single Revolute link then is about as easy as you can get. We're going to analyse this linkage using, first of all, by putting appropriate frames on the linkage, and then analyse it using homogeneous transformations. So let's think about where we could put useful frames. Well, first of all, here is the robot, here is the base, here is the joint. It's got a length L1. The length can be, the arm can be moved around by θ1. So the first thing we could do is say, let's put, we want to put something at the base, right? We need to have a base frame, and we're going to put it such that the z-axis corresponds to the axis of the joint, right? That's following Denavit-Hartenberg. And in this case, I'm choosing X to go forward, so it's going in the direction of the arm. And then basically you're not free to, you've got to put Y in such that we're following the right-hand rule. So that's fine. We've got the base. Now what we want to do is we want to worry about the fact that this thing can rotate, and we're going to have another frame that we're going to line up such that X now goes along the displacement. In fact, we need to do that because we want X to coincide with the z-axis. Basically, it's got to cut into it. So what we do with this frame then is now we can account for the fact that this thing's going to rotate by θ1. But that's not the end of the story, because now what we care about is accounting for the fact that we've got this length L1. So we want to move to the end of this little arm, to the location of the end effector, so we can stick on another frame there. In this case, the easiest, normally this would also be then feeding into another arm and another section and another link and what have you. I've just put, just to make life easy, Z is now carrying on being parallel to what it was before, as if it would be another joint. It's not actually another joint, but you can see then we've got X carrying on in the direction of the linkage, and Y goes in appropriately in order to follow the right-hand rule. So let's now think about going from frame 0 to frame 1. In fact, what we care about is going from frame 1 to frame 0, I should say, because we are interested in everything being represented back in the base frame, right? So we want to know how do we get between these two frames. So first of all, we notice that there's a rotation, right? So there's a rotation of θ around Z1. So we have a nice rotation matrix, and we know from what we've already done, in order to map the frame 1 to the frame 0, that relates to this rotation matrix, and we've got a positive θ, if we take it as it's drawn here, round in this direction, because that follows the right-hand rule. So we've got a rotation around the z-axis. We've got no translation at all, though. So the simple transformation which takes us from frame 1 to frame 0, the homogeneous transformation, is the z-axis rotation matrix. And what we do, well, that's the component there, the 3x3 rotation matrix. The 3x1 translation of 0, right, 0, 0, 0, and then the bottom line again is always 0, 0, 0, 1. So that will map from frame 1 to frame 0. Now, we've got our frame 2 and we've got our frame 1. How do we map between those? Well, we can immediately see, right, there is no rotation at all, right? It's just translation, and it's translating along, in fact, the x-axis. And it's translating by the length of that particular link, which is L1. So we've got a translation then between, in order to get to, to x2 from x1. So therefore, the translation we need is going to be in the x component of magnitude L1, and there's nothing translated in y, and there's nothing translated in z. So in this case, if we want to use homogeneous transformations, as we want to do that so we can multiply things together and it's nice and easy to get the final result, this time we put in the homogeneous transformation for this no rotation, so it's going to be the identity matrix, and then we have the translation component, this 3x1 translation of the component in the homogeneous matrix is now just going to be L1, 0, 0. So it's just shifting in X. And of course, the last row is 0, 0, 0, 1 as always. So now we've got those two transformations to get from frame 1 to frame 0 and frame 2 to frame 1. All we need to do is multiply them together, right? So this then will give us, this gives us 2 to 1 and then 1 to 0. So we can multiply those two matrices together that we've just derived, and we end up with the homogeneous transformation, which will map a point in frame 2 directly to frame 0 at the base. So just to point out what's important about that, if we want to actually know where the endpoint, this endpoint is going to be in zero in terms of z0, right? What we would do is say, well, let's take a point. Let's take the origin here, because that is the location of the endpoint in the frame 2, right? That's the point in frame 2 gives us the endpoint. If we then multiply that, well, with this transformation matrix, that's going to give us the location of the endpoint in frames in terms of frame 0, right? So that's what we would do. We just multiply those things together, and we'd end up with, in fact, it's quite obvious what you're going to end up with. You're just going to end up with this part of it, right? You'll just end up with this part of it. In fact, you can look at this matrix and immediately say, you know, this represents, as we know, a rotation, right? This rotation. And then on top of that, we get this shift, right? So because it's always rotation and then shift. But this is just going through it from first principles. If you put in that point as 0, 0, 0 in frame 2 and multiply that with your transformation matrix, it tells you what point you get in terms of frame 0. And that's exactly what we've got. We've got L1 cos theta 1, L1 sine theta 1, 0, because obviously it's not moving around in Z, so that stays put. Let's now think about adding another link and doing pretty much the same thing again. A single link is, like I said, about the simplest thing you can do, but you can still, you know, you can learn a bit from doing a simple system. And then the other thing is, you know, do look at where the endpoint ends up when you're doing these things. Make sure that, you know, have you done, let's say you did a big long equation with lots of linkages, does it actually make sense what you end up with? So you can use these nice little methods as a way to sort of check that you're doing the right thing. Let's now think about a two-link system, two Revolute links, which are basically, it's a plane, in a plane, I should say. We're only rotating round z-axis, z-axi, that's going to be basically into the plane. Oops. So, frame 0 again, we're going to stick frame, well, in fact it's coming out of the plane, the z0 is coming out. So what we've got here now is we've put our base frame in again, because we care about, you know, where's this thing going to be put down, right? So we need a base frame. So that's the first frame put in. Now we need to put the second one in. So that, again, just like we did before, we need to account for the fact that this is rotating by theta 1, and it's got a length L1. So first of all, we're just going to deal with the rotation, and then we'll put the next frame in, which is basically a translated version of that, right? So we need that copied and moved along to the next location, and that will then account for this thing at the elbow. But then we need another frame to account for theta 2, right? So we've accounted for theta 1 and we've accounted for L1 doing this. Now we need to make sure that we're pointing in the direction of the second linkage, right? So we need to put in another frame where we're now pointing, again, we're rotating around axis, so Z comes out, but now we're pointing along the length again with X, which is always a good thing. And again, you see that X is always going to intersect with a Z, which is also what we wanted. But even that isn't the last of the story, because that's not accounting for the fact that the final endpoint's also shifted by L2 further along, right? So we put the final frame now in at the endpoint, again, we're lining up the z-axis like we did before, because there's no reason not to. X is now pointing in the same direction, and X will intersect our previous Z as well, which is also nice. So looking at them all together, it looks a bit of a mess. So let's do them in stages, right? Going from 1 to 0, again, we just see that this is a rotation of theta around the Z-axis, right? So a rotation from 1 to 0. So the frames are actually coincident in terms of their origin, so there is no translation. So our homogeneous transformation for 1 to 0, just like it was before, is just the rotation part around the z-axis and no shift. Okay. Now we're going to do from frame 2 to frame 1, and this is just like we did before as well, so it's precisely the same result. In this particular case, obviously the frames haven't rotated, so they're pointing in the same direction, but there's a translation along the x-axis of L1. So we get a translation of L1. So identity matrix for a rotational component, L1, 0, 0 for the translation component, and then we've built the homogeneous matrix up for going between 2 and 1, just exactly like we did before, actually. And now we have to do the next bit. Now we're sticking on the bits to account for the fact that we've got another joint. So this is, again, very similar to the first joint. We've got frame 3, which is a rotated version of frame 2, but it doesn't shift. So we've got, again, a rotation around the z-axis, and that's the nice thing about using Denavit-Hartenberg. It's always going to be around the z-axis if it's going to be the actuating joint of the system. We put that value together with theta 2 this time. Again, there's no translation because the origins are on top of each other. So this time we have a homogeneous transformation, and this is composed of the rotation around this second axis by theta 2 and no shift. Finally, we need to get to the endpoint, right? So we need to, again, just do pretty much what we did for the first linkage. We need to just move along, right? This is just moving along the x-axis, and it's not rotating. So there's no rotation. We've got a rotation matrix, which is actually identity matrix. There is a translation, and this time it's along the x-axis again, along x3, but it's of length L2, right? So we've now got identity matrix for the overall transformation and the homogeneous transformation. We've got a shift of L2 in x, and basically that's it. And now if we want to know how to get from the endpoint to the base, 4 to 0, we have to go from 4 to 3, 3 to 2, 2 to 1, 1 to 0. And because it's homogeneous transformation matrix format, we can just multiply them together and we'll get the result. Okay, so you can multiply those together. It's a bit tedious to do it by hand. I did it basically in Matlab, and you simplify. Obviously, you can't do that in an exam normally, but basically, I would I'm doing a question on this kind of stuff. I care more about you getting this bit, right? I want you to get the bits which are realistic, because this is starting to get tedious, and this is very tedious to get that by hand. So don't worry about that too much. Obviously, you get a couple more marks if that was the question. Give me the answer, then you will get more marks for doing more. But it's really the principle I really care about. And this is just doing it all in Matlab. This is just for sort of reference purposes. So we're building an identity matrix 3 by 3. You can use the I command, putting in L1 and L2 as being symbolic, theta 1 and theta 2 being symbolic. Then I'm building rotation matrix around Z by theta 1, building the first homogeneous transformation, first link translation vector, and then the overall homogeneous H12. Then we do, just you can see what's going on there. It's the rotation matrix, then it's H23 and H34, and then doing the overall calculation, multiplying them all together, 3, 4, 2, 3, 1, 2, 0, 1. And then using Matlab simplify in order to get a nice result that comes out that you can understand more easily. So we can find the endpoint quite easily then by looking. Well, first of all we can actually just look at the matrix, and I can look at that and tell you it's going to be due to the translational part at the end, right? The translational part at the end, this term, and this term, that's going to be the endpoint in the frame of the base. But to do it in a more rigorous way, you could say let's just multiply it by the origin, which then represents the frame at the endpoint, the origin in the frame of the endpoint, which is obviously 0, 0, 0, and it's 1 because it's got to be done with homogeneous points. Multiply that out, and that's exactly what you can just see directly from this term, and this term. That's this, this, and this. That tells you where the endpoint is in terms of the coordinate frame of the base. And that's effectively giving you forward kinematics. Right? You give it the theta. L1 and L2 are fixed, and there you have it. I think they're all theta 1 for some reason. Maybe that's something wrong. I think it is. I think there's some of those should be theta 2s. So we see that. Yeah, definitely. So this is correct. That's wrong. So we see that the endpoint then, the x and the y values are given by L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and so on, which you can also derive. In fact, we've done that kind of derivation in a more simple way by hand before.